This equation is arguably the most beautiful equation in all of mathematics. It links between three fascinating constants: pi, which is the circumference over the diameter of any circle; Euler constant, which is the limit of the compound interest on $1 with 100% yearly interest; and I, the imaginary number, which is the square root of -1. Welcome to Infinite Synthetica, and today we will talk about imaginary numbers. In the year 1545, Gerolamo Cardano discovered the solution of the cubic equation of the form x cubed plus ax plus b equal 0. And this is the form of the solution. It's very good, but with a little problem. Let's take an example. Consider the equation x cubed minus 15x minus 4 equals 0. It's easy to see that x equals 4 is a solution to this equation, but let's use Cardano's formula to calculate the solution. Computing delta, we get minus 4 over 2 squared plus minus 15 over 3 cubed, which equals 4 minus 125, which equals minus 121. And this is the problem with Cardano's formula. We get the square root of negative numbers, which was meaningless in that time. So Cardano's formula fails to find the right solution. At this time, Raphael Mambeli intervened. He continued the computation, ignoring the square root of negative numbers. He realized that 2 plus the square root of -1 cube is equals to 2 plus the square root of minus 121. Also, 2 minus the square root of -1 cube is equal to 2 minus the square root of minus 121, which simplifies Cardano's formula. At the end, the square of the negative numbers cancel out and we get the right solution, which is x equal 4. So let's recap. We had a problem, which is finding the solution for the cubic equation. In the process of solving our problem, we use this meaningless numbers, which we will call imaginary numbers. And at the end, we find the right solution. With the help of this example, we just scratched the surface of the usefulness of the imaginary numbers. Mathematicians had to decide what to do with these weird numbers. In one hand, they are super useful. In the other, no one have any intuition what they could mean. So, embrace them or discard them. Mathematicians had decided that the imaginary numbers are too useful to discard. So now they need to find a proper way to define them. A mathematician called Wallace proposed a way to think about complex numbers. By the way, complex numbers are a combination of real numbers and imaginary ones. For example, I, 2 plus I, minus 3 minus 2I, minus 1. Wallace suggested that we should think about the real part of the complex numbers as usual real numbers in the number line, and the imaginary part as a vertical distance corresponding to the value of the imaginary part. This idea by Wallace was strengthened and deepened by separate mathematicians, Wessel, Argrand, and Gauss. They suggested that we should think about complex numbers as points in a two-dimensional space. The horizontal axis is for the real part, and the vertical axis is for the imaginary part. All these mathematicians suggested ways to represent complex numbers, but technically we didn't solve the problem yet. And then comes William Hamilton. He did not suggest a way to represent complex numbers. Instead, he presented a way to define complex numbers. He defined them as coordinates in a two-dimensional space. So, for example, I is defined as the point with the coordinates 0, 1, 2 plus I with the point 2, 1. So Hamilton is different from the other mathematicians in the way that he don't think about complex numbers as a new kind of numbers, but as just points in a two-dimensional space. So he thought that complex numbers are not special in their own, but in the way that we use them. Now that we are convinced of the importance of complex numbers, our next mission is to extend the regular mathematical functions to accept complex numbers. But how? Using the Taylor definition for those functions is a clever idea to extend the domain of those functions to accept complex numbers. It's easy to work out that the exponential of iz equals the cosine of z plus I sine of z. Z could be a real number or a complex number. And that is the power behind our approach. Plug in pi in our equation and voila, we get the famous equation, Euler Identity. The exponential of I of pi equals -1. This part is for the curious from you. I will explain briefly the steps to solving a cubic equation. So, the general form, ax cubed plus bx squared plus cx plus d equals 0. The first step called depressing. In it, we transform the general form to the depressed form, which is x cubed plus ax plus b equals 0. And we do that by substituting x, which is the variable in the general equation, by t minus b over 3a. T is the variable in the depressed form. The second step is computing a bunch of expressions, delta, epsilon 1, epsilon 2, and beta. The final step is computing 3 potential solutions for this equation, which are of the form x1 equals the cubic root of alpha plus the cubic root of beta. x2 equals epsilon 1 times the cubic root of alpha plus epsilon 2 times the cubic root of beta. x3 epsilon 2 times the cubic root of alpha plus epsilon 1 times the cubic root of beta. I want to share with you the big picture of the universe of numbers, if you like, and the set of all complex numbers and where it sits within. Let's begin by Zermelo-Fraenkel set theory, which is regarded by many mathematicians as an axiomatic set theory strong enough to hold the weight of all mathematics. In ZFC, which is Zermelo-Fraenkel set theory plus the axiom of choice, we just need to accept the empty set as a primitive object. And from the axioms of ZFC, we could construct the set of natural numbers. For example, we could do that by recursively invoking the pairing axiom, representing the number 0 by the empty set, 1 by the set containing the empty set, 2 by the set containing the set containing the empty set, and so on. So we create new sets of numbers, and using the natural numbers, we could easily construct the relative numbers, and so on and so on. We create new numbers from previously constructed numbers, and by that, we see that Hamilton's suggestion for how to construct complex numbers is the next logical step. Although this construction of numbers is aesthetic and beautiful, we need to only accept sets as a primitive mathematical object in the ZFC axioms. It strips the numbers from their magic. They appear just as labels, which has huge philosophical issues. For example, there is no difference from the label 0 in the empty set. So the proposition 0 belongs to 1 is a totally true proposition within our system, which make no sense intuitively. So is Platonism the right way to go? This is a discussion for another day. Let's wrap up our video by a beautiful Leibnitz quote. The divine spirit found a sublime outlet in that wonder of analysis, that portent of the ideal world, that amphibian between being and not being, which we call the imaginary root of negative unity. If you like the video, consider supporting the channel, and see you in the next video.